Hello, everyone. This is another lecture for your embedded systems and applications. This lecture covers the DC motor, speed, and direction control. Sometimes it is an important section when it comes for robotics and motor control applications. So speed control of DC motors are basically done using pulse width modulation, also known as PWM. So PWM is used to generate a variable DC voltage using digital. Generating variable speed, variable output voltage can be done using digital to analog converter, but that needs some special hardware. But in PWM, we are dealing with average voltage. So we are controlling, generating a square wave signal with different depth ratio to generate a variable output DC voltage. Now, so this is a very simple example of that. So you can see this is a square wave signal, and this is a turn on period, that is T on, and this is the turn off period, T off, right? So the total time period of this waveform is capital T. So the frequency, then you can calculate 1 upon capital T. So that is the frequency of this PWM signal. And so the duty ratio is known as the amount of portion that is this waveform is turned on during this time period, right? So T duty ratio is denoted as D. D is the ratio of T on, the on time, with respect to the total period. So the T can be within the range of 0, which means like this portion is there's no turn on period, which means the signal is always 0. And if the D is 1, which means like this period is fully turned on. So D can be any value between 0 to 1. By adjusting the D, we can get a variable output voltage. For example, now, if you have the D is 0, the output voltage, average output voltage will be 0. If you have the D as 1, the average output voltage is the same voltage here, this voltage V. And so by changing the D, we can increase or decrease the average voltage. So in order to calculate the average voltage of this waveform, we can take this total area and divide it by this period, right? So you can take this the turn on period here is this voltage V into T on, so that will give this this area, and plus this area is, you know, like the voltage is 0 into T off is 0, divided by this period capital T. So this term goes off, which means T on divided by capital T divided into V, which is dV. So the average voltage is D into this voltage V, right? This is the peak value of this waveform. So you can see, like, when D is 0, the V average is 0. So when the D is 1, the average voltage is 1, simply V, right? So the any value like can be obtained by changing the duty ratio. So it can be from 0 to VCC, or if the supply voltage is VCC, you can achieve a new average value. So this method is used to speed control of DC motors and to adjust the brightness of lamps and servo motor drives. So if you apply this waveform to a DC motor, you can control, like, if by adjusting the duty ratio D, you can increase or decrease the speed of the motor. So if the D is high, the motor is supplied with average voltage, which is quite large. If the D is 0, the mode is turned off. And for any average value between from supply voltage to 0, the motor speed can be changed, right? So when the D is 0, the motor is turned off. When the D is 1, the motor is fully turned on. For any other fully turned on, means it runs in the maximum speed. And for by changing the duty ratio, so the average voltage will be adjusted the same as the motor speed. So this mechanism is used to basically for DC motors, which is the application that I'm discussing in this lecture. So we can get some more example about how this duty ratio changes. So here you can see 0 duty ratio, which means the average voltage is 0. If you have 25 duty cycles within this period, this periodic time, 1/4 of the cycle is turned on, which is 25% of duty cycle. 50% duty cycle is half on and half off. 75 duty cycle is 2/3, 3/4 of this period is turned on, and 1/4 is turned off. 100% duty cycle is the fully supply voltage is given. Right. So if you want to interface a DC motor with a microcontroller, so you can't directly couple the microcontroller to a DC motor, because we know the microcontroller digital output pin can drive only a very small current, typically 40 milliamps. So DC motors require the currents in the range of amps range, right? 1 amperes, 2 ampere, like that. So in that case, we need to have some sort of a DC motor driver. So basically we can use a H-bit driver. So its job is to get this control signal from the MCU, because it can accept any control signal within 0 to 40 amps, but generate a current from 1 amps to or any other amps related to this motor based on the capability of the H-bridge. So accepting any digital signals, pulses from the microcontroller. So this and generating current, high current output from to drive the motor, typically 1 amps, right? This signal can be only 40 milliamp, but this can be generated as a 1 amp. So it is like an amplifier, right? Obtaining a voltage signal and generating a voltage signal which can drive a large current. So the H-bridge also requires some sort of power. So it needs one part of the H-bridge needs 5 volt to for its control signals, because MCU generates control signals. So there's a control part of the H-bridge which needs to deal with this control signals coming from the microcontroller, right? So that needs 5 volt. And there's another part that needs to deal with the motor. So the motor is powered with, like there are motors with 6 volt, 12 volt, 24 volt. Based on the motor voltage, you have to provide this supply voltage. So that supply voltage is to deal with this motor, and this control 5 volt is to deal with this side of the microcontroller. So accepting this voltage here and controlling the DC motor with this voltage, right? This plus Vs can be 6 volt, 12 volt, 24 volt, and can go up to 35 volt depending upon the applications and depending upon the H-bridge type. And so H-bridge has a different internal hardware, but you have to provide some sort of fast recovery diodes apart from the H-bridge in order to protect the H-bridge from inductive switching, because the motor is something like a load with resistance and inductance, right? Equivalent circuit. So there's an inductive load, so you have to have some kind of freewheeling diodes when switching inductive load. So you need to have fast recovery diodes when you're using HBridge. So I will explain how to use them. So for now, remember, this is how we couple the microcontroller to a motor. In the market, you can just buy HBridge drivers. Even for Arduino, there are some HBridge shields. So you just need to couple the shields to the motor and to the Arduino. But if you use a HBridge type IC, you would have to add some external components and build your own HBridge. But there are some built-on shields, HBridge shields, you can buy from the market. So that is more easier than buying an IC and build some HBridge by yourself. All right. Now you can see HBridge controller. So this is the internal hardware of a HBridge controller. We can see. So it has 4 transistors, and the motor is connected to the bridge in this way, right? So in the middle of this leg, and the middle of this leg, the motor is connected. So the HBridge should be powered with the voltage that is required to drive the motor. This is that VS that I was talking about, this VS, right? So this is the power side of the motor. So you have to provide this power to this motor. And this A, B, C, and D are the control signals coming from the microcontroller. So Q1, Q2, Q3, and Q4 are the transistors, and D1, D2, D3, and D4 are the freewheeling diode that is required to connect when you're switching this kind of inductive switches like DC motors. So they are freewheeling diodes. You must connect them in order to protect the HBridge from inductive switching and high voltage spikes. Right. So think about, like, if you want to rotate the motor in the clockwise direction, this way. So in that case, we need to have plus and minus in this way, right? If you want to rotate the motor in the counterclockwise in this way, you need to provide plus in this side and minus in this side, changing the polarity. So you know, like in the DC motor, if you change the polarity, the direction will be changed. Okay, so now let's take a look at the clockwise direction. So here you need to turn on Q1 and Q2. So Q1 is turned on, so you have to provide 5 volt supply to A, and Q2 you have to provide 5 volt supply from the microcontroller. Then you can turn on these 2 transistors. So when the transistor turn on, so it is just short circuiting its collector and emitter and make a short circuit path here. And this impedance will be very low, like a 0, as you can assume 0 ohm, like short circuiting using a wire. And this is also short circuited to the ground. Okay. The diode direction is opposite, so there's no current flowing through the diode, right? So diode is reverse bias. Now the current can come from this VS. This is something like a battery. So the current can come from this side through this transistor and through the motor and go back to here to the ground. So the current path is completed. So the motor is now running in the clockwise direction because Q1 and Q2 are turned on and Q3 and Q4 are turned off, right? So you have to provide logic 0 here to this one and logic 0 to here, 5 volt to this one and 5 volt to this one. So these 2 transistors are on, the current path is from here to here. And then, so this side goes plus because VS is just appearing here, and once this is short circuiting, the ground is appearing here. Right, so this is how you turn on the motor in the forward direction, the clockwise direction. And if you want to stop the motor, what you can do is just this is also 0 volt and this is also 0 volt. It was there, so this was in 5 volt, right? So if you turned off, so you just put 0 volt here and 0 volt here, So this transistor will be turned off, right? So there's no longer current can flow through there. But like the motor is like an inductive load. So it takes some sort of inbuilt magnetic field. So that takes some time to disappear, right? So which means like it needs some time to discharge the magnetic field, and so there will be some sort of current flow in the motor for some time until this magnetic field is disappeared. So that current is flowing in the same way than the previous current. So the previous current was flowing here. Now this current is coming to here, and like all the transistors are now turned off, right? Because these two guys are turned off from the initial state, but these two are turned on. Now they are turned off, right? This is turned off now, Q1 and Q2. So the current has no way of flowing there, but it can only now, because the current cannot go through this diode because it's a reverse bias. So the now current can go through this diode, right? Because the current direction is here. So the current can go through this diode, through the VS. And so this is acting as a battery, it's a battery. Go through the battery and comes back to the ground and comes back again. It cannot go to the same point where it is started. So it has to go to the this point, right? So D2 is not an option. So it can go through D4 and comes back and making this circuit completed. So it has to go through by charging the battery. So the battery will be charged with the stored energy of the motor in its magnetic field, and the motor will be turned off after some time. But it takes some period to completely turn off the motor. And if you want to turn off the motor really fast, so you can just turn on Q1 and D3. D3 is you don't need to do any switching, but it is a diode. So when you turn on Q1, so this transistor is turned on, so the current can and D3 is on, so the current can go through here, through this path, and return back to here, right? So you are short circuiting this the motor terminal, so that will discharge the magnetic field quickly and helps to stop the motor fast. Right. So the anti-clockwise operation is entirely opposite than what I have discussed. So if you want to anti-clockwise, you have to provide plus here and minus here, right? So they need to rotate in this way. Right. So in that case, you need to turn on Q3 and Q4. Q3 is turned on, so it is short circuiting, and Q4 is turned on. And these two guys are turned off. Right. Now the current can flow from VS through this Q3 diode and through the motor and through the Q4 and return back to the ground. Okay. And if you want to stop the motor, what you can do is just turn off all these switches. This is turned off and this is turned off. And the current flow was in this direction. So the magnetic field is there. So it needs some time to disappear. So this motor now can go through the D1 diode and through the battery and through the battery and return back to the ground and coming back from D2 and returning back here and making the circuit completed. Right, so D1 and D2 are used to discharge the magnetic field and the motor will be turned off after some time. Right, and if you want to turn the motor so fast, what you can do is you can just you can turn on Q4 diode And so in that case, the current was flowing in this direction. So the current will go through Q4 and returning back to this point and come back to D2 diode and make the circuit completed. So it is like a just short circuit in the motor through this path. So that will discharge the magnetic field so quickly. And so that's the basic operation of this H-bridge. And one interesting point is you should never turn on, like when you do the microcontroller programming, do not turn on Q1 and Q4 at the same time, right? So if you provide logic 5 to this pin and logic 5 to this pin, what it does is short circuit, turn on this transistor and this transistor. That will short circuit the battery towards this path, right? That will allow a large current to short circuit current to flowing through these transistors, and that will destroy these transistors, right? Destroy these two transistors, and you can't use the H-bridge again, right? And the same thing happens when you turn on these two transistors at the same time. Therefore, when you're turning on any motor, make sure there's use some dead time, like so you turn this guy 5 volt, right? And at the same time, you have to turn on this guy. And when you turn on this guy, like do not turn on, like this is the next signal. So you have to start at the point that that this guy turned off, right? But do not turn on, keep this turn on period beyond this point, because that will, there's a time period where both transistors are turned on. So in order to avoid that, we can have some kind of like a dead time. So what it does is like, I will draw it again. So you know, like this transistor turn on here and turn off here. The next time you have to turn on this transistor somewhere here, right? But for safe operation, you keep some small delay and then turn on, right? Like this delay may be like a 5 microseconds, or depending upon the speed of your PWM signal. If it is a fast signal, you can reduce this, but if it is a large signal, you can have some sort of like a very small gap between here. So then you know 100%ly these two guys are not turning on at the same time, because the signals start from somewhere here, not here, right? There's no overlap between two signals, and then we are pretty much sure Q1 and Q4 are not turned on. Same thing applied to Q3 and Q2. Otherwise, the H-bridge will be destroyed and you can no longer use it. And this is a typical example of H-bridge. So this is L298 H-bridge. So this is this IC. There's a surface mount version as well. And so this is the datasheet description. There are some pins, so you can see. First pin is like you have to provide the motor voltage, that is Vs, and the ground terminal. So that is the required supply for motor. And for your control signals coming from the microcontroller, you have to provide +5 voltage and this ground, right? So this is the 5 volt supply and this is the motor supply. So which I have explained in this here, right? So 5 volt for to control deal with the microcontroller and Vs to deal with the motor. Right, so this voltage is the motor voltage. If the motor is voltage is 12 volts, you can apply 12 volts here. If the microcontroller dealing with 5 volts, you can apply 5 volts. And this is there are two H bridges. This one to have one motor and another motor to you can interface to this side. So if you're using like a robot or something, it can control two wheels and having two motors. If you're using a single motor for any application, you can use one side of this IC to control. So I'm just explaining one side. Here, assume like we have three control signals. First one is enable, ENA, to enable this edge bridge, right? If you you had provide 5 volt here, then only this edge bridge will be activated. And depending on this in 1 and in 2, you can turn on these 2 transistors, like I mentioned in the previous slide, to change the direction of the motor. Right, so there's the 2 sensor resistors, shunt resistors, that is used to generate analog voltage, which is proportional to the motor current, right? So the motor current is proportional to the driving PWM signal. So by getting this analog voltage, you can you know this motor because this voltage appearing here is proportional to the motor current into this resistance. So you know this resistance. So if you use like a 0.1 ohm resistance or 0.01 ohm, and if you know the voltage, you know you can reverse calculate the current of the motor. So you can couple this voltage signal to the ADC channel of a microcontroller, and you can convert and find this voltage. And if you know the resistance, you can determine the amount of motor current, and that can be used for overload shutdown or any protection schemes, or sometimes to monitor the motor current for safety. And this is how you interface this motor. So this point should be connected to the one side of the motor, and this point should be connected to the other side. And your freewheeling diode should be connected in this manner. And the top of the freewheeling diodes again goes to this VS, and the bottom of the freewheeling diodes again it goes to connected to this point. Right? Then you can achieve this mixed motor driver, and we can just take a look at how this operates. Okay, so if you turn on so every time if this is 5 volt, and this should be 0 volt. Okay, so I'm just talking about one single example. Assume like IN1 is 5, so IN2 should be 0 volt. They should be in opposite polarity, opposite logic. Okay, in that case, you know, like ENA is 5 volts, so this is 1. This is logic 1, and this is logic 1. And here also this is logic 1, and this is logic 1. And IN1 is 5 volts, so this is logic 1, and this is an AND gate, so this should be logic 1, which means this transistor is now turned on. And here you can see this is logic 1, but there's a NOT gate, which means this is 0. And 0 and 1 is 0. This transistor is turned off. Here, this is 1 and this is 1, but this is NOT gate, and this is 0, and this is 0. Output is 0, and this transistor is turned on. And this is 1, and sorry, this one is 0, and this is a NOT gate. This one is this is 0, and this is 0, and this is 1. It's a NOT gate, and 1 and 1 it is 1, and this transistor is turned on. And here you can see this is 0, and this is 0, and NOT of that is 0, and this transistor is turned off. So you know this Q1 and Q2 are turned on, so that now the current can flow from this point coming to Q1 and goes to this path through this transistor and appearing plus here, mode returning from here, comes to here, goes through this transistor from this point to the ground. So this side is negative. So it is a clockwise rotation, right? The other ways, the other logic sequences having 0 volt here and 5 volt here. Okay, So in that case, now enable is always true. This is 1 and this is 1. This is 1 and this is 1. Now we know like this one is 0 and this is 0 and this is 0 and this transistor is turned on. And this is 0, but this is not yet, and this is 1 and 1 and 1, this is 1. So this transistor is turned on. So similar logic is applied. You know, this is 5 and this is 1 and this is 0 and this is 0 and this transistor is turned off, and this is 1 and this is 1, it is 1 and this transistor is turned off. Now you know the current can flowing from true VS comes to here, and true Q3 transistor comes to this point and goes to here, goes to this motor, and this side goes plus and this side goes minus, comes here, come to this point, and through this it can return to the ground. Right, so it is anti-clockwise direction of the motor. Okay, so this is the simple way of change the direction. So now if you want to change the speed, what you can do? So in that case, you have to do is assume like you want to have the forward rotation with the PWM signal. Now you can do is I want to forward clockwise direction, right? So I can just provide 5 volt here and 0 volt here. And for the enable, I can provide this PWM signal with different duty ratios, right? So if you provide 50% duty ratio of the enable, so the motor speed will be half. If you provide 0 duty ratio, the motor is fully turned off because enable is always 0. If you provide 100% duty ratio, the motor will be always turned on. So that's how you achieve this speed, change the speed of the motor with this direction. If you want to change the direction, you have to change the logic in these 2 pins and apply the PWM signal. And so this PWM can be generated either using if you have a microcontroller. So the PWM generating, there is a dedicated section either for timers and counters. There's a pin for that. You can couple to that pin and generate a PWM signal and control the speed of the motor. And if you want to drive another motor, you can connect the microcontroller another PWM pin and couple to it here. If you want to have the same PWM signals to be here, you can couple the same PWM signal here, because if you wish to have the same speed of the other motor, you just need to have one single PWM signal. So that is the hardware and how you interface. Now, this is how you control. So I mentioned enable is if you want to enable, you have to provide 5 volt. If you want to enable the bridge A, you have to provide 5 volt. If you want to enable bridge B, you have to provide 5 volt here. And out 1 and out these ones, right? Out 1, pin number 2 and 3 is for this bridge A. Sorry, there's a mistake here. Out 1 and out 2. And out 3 and out 4 are for motor number 2. Right. So out 3 and 4 are to drive the other motor. So you must connect the freewheeling diodes. The freewheeling diode is example is 1N4148. This is that one. And so RSA and RSB are feedback resistors, like I mentioned. You can have this to observe the motor current. And if you want to drive the motor in the clockwise direction, IN1, you have to enable the bridge, and IN1 should be logic high, this one high, and this is 0, and enable this high, so it will rotate the motor in this way. And if you want to have the anti-clockwise rotation, so IN2 should be high. So this is high, this is 0, and this is high. And if you want to stop the motor without an issue, so you can just disable all these pins, so it will be discharged through these freewheeling diodes, but it takes some time. But if you want to have fast stop while keeping the enable through, you can have IN1 and IN2 both turn on, right? So in that scenario, what is happening is this is 5 volt, and if you apply 5 volt here and 5 volt here, right? But remember, like the protection is already inbuilt. If you look at the previous example, there was no any protection scheme. Now, in this transistor, you can see there's a NOT gate, which means like even though you put 5 volt here, both guys will not be turned on simultaneously because opposite logic is applied, right? If you turn on both of them, due to this NOT gate, this one will be turned off, right? But for fast stop, we have to turn on everything, right? Let's take a look at what will happen. So, assume that motor was running in this direction, right? Plus and minus clockwise rotation. Let's see that you want to stop the motor fast. So, this is logic 1, right? This is 1. Enable this 1. And this is also 1. And this one is 1. So this transistor will be turned on. And this is 1, but this is 0, and this transistor will be 0. And this is 5 volt. And this is 1, but this is 0, and this transistor will be turned off. And this is 1 again, and this is 1, which means this transistor is turned on. So these two transistors will be turned on. So in that case, what is happening is, like this current, I will draw in a different color. So that can come to this point, comes here, and on this transistor, so this current can come from here, from here. But like the transistor is not allowing the current to flow in this way, right? So there's no way of going through this transistor, but like Q3 transistor is here, but there's a diode D3, like same diode. I can draw that diode like this because it's the same diode connecting to this point and this point, right? D3, I'm just mirroring that diode, right? One side of the D3 goes to plus VCC, same here, and the other side goes to this common point of the motor, that is this one, right? So I'm just mirroring this diode for the ease of the explanation. So now, like even though you turn on, the current cannot go through emitter to the collector, right? So even though you turn on, there's no point. But that D3 diode can allowing you to pass that current through this Q and here and short circuit in the terminals of the motor, right? Actually, it is going through this D3 diode, but for easiness of the explanation, I'm just repeated that diode here. So you can see like the diode is just the motor is just short circuited, and it is turned off in a fast manner. So even though if you have the motor is running in the other way, same principle happens. So only different diode will be into the application, this transistor and maybe D1 will be turned on, and keeping the motor current circulating and helping to disappear the magnetic field and stop the motor real fast. Okay, right. So if you use Arduino board, you can generate this PWM signals using PWM function. So PWM has nothing to do with analog pins, right? So there are some dedicated pins for PWM, pin number 3, 5, 6, 9, 10, and 11 in most Arduino boards. So you can use the PWM to adjust the average output voltage across the pin. So the PWM frequency in most pins are 490 hertz. Frequencies this. If you have this kind of waveform, this is the periodic time, and the frequency is 1/t, right? So most of the time the frequency is 490 hertz. If you want a fast, like you can achieve the same duty, like this is 50% duty ratio, half on and half off, but you can achieve the same duty ratio with another like a high frequency, like if you double the frequency, like this waveform is also having the 50% duty ratio, but you can see that the frequency is double, right? So 50% duty ratio, but the frequency is double. This frequency is 980. So you can select the frequency based on your applications. If you want like a real high fast operations, you can use this pin number 5 and 6. If you want slow operations, if the speed is not a factor, speed has nothing to deal with the the frequency doesn't have nothing to deal with the speed, but due to this inductance and everything, sometimes you have to select the required frequency, but the duty ratio is the thing that you can have to control the speed, right? It will work for both of the frequencies, right? But so by changing the duty ratio, then you can adjust the speed. But changing the right frequencies depending upon the motor inductance and everything. But at this stage, forget about that. Assume like it will work for both frequencies. So if you use Arduino IDE, so in order to generate a PWM signal, you don't need to worry about like much more complicated details that we learned in timers and counters. You can just use this function. So it will do the all hard work, like generating the PWM signal. But you have to provide these arguments, which pin that you are using, pin number 3, 5, 6, 9, 10. So depending upon the pin, the frequency of the signal will be changed. If you want to have slow operations, you can either use 3, 6, or any other pin. And this value is the duty ratio, so D, right? So the D can be changed from 0 to 255. 255 is the, like when the D is 1, and when the 0 is when the D is 0, right? So 0% duty cycle, the pin number and 0, 100% duty cycle, pin number and 255. So you can adjust the duty ratio from 0 to 1, and with the resolution of 255, because this is split into 255 segments, and you can adjust the duty ratio in segments of 1/255. Right, that's the resolution of this speed, which means you can achieve 256 different, including 0 and 255, 256 different speeds by using this analog write function. Right, so this is the hardware arrangement if you're using Arduino Uno board. You can see this is the H-bridge L298. The out 1 and out 2 is connected to the motor, and the freewheeling diodes are connected in this way. One side goes to the positive side and the other side goes to the ground. This is your supply for the motor and the VS of the chip. And this 5 volt is to supply the controlling part of the chip, this 2L298 and the ground. Make sure that you have to have common ground for the battery, this control side, and this power side or the motor driving side. All should be connected to this common ground, and the Arduino ground also should be common, right? So, like the Arduino also has a ground, which is not shown here, right? So Arduino ground must be connected to this the common ground of the circuit, otherwise it won't work, right? Make sure you connect the ground of the Arduino to the ground, because everyone has to have a common ground. Then you can connect this this one of the digital pin. You can see this this symbol is for PWM, right? If you use any sort of these pins, it is dedicated for PWM generation. So here you can see I have used this this one, pin number 9, which is connected to the ENA, right? ENA goes and comes to this one, like pin number 9, which is for generating PWM. So by adjusting this one, using this function, I can, by putting this pin number to 9 and the duty ratio to any value between 0 to 255, I can control the speed of the motor. And other two, IN1 and IN2, these two inputs are connected to pin number 7 and pin number 8. So now I have all the control signals are connected. And I can use this simple code to rotate the motor in full speed. You can see, like, first thing is I have to set this ENA to logic high. You can see pin mode 9. Sorry, make this pin, all these pins as outputs. Like these are digital output pins, right? You are not taking any inputs. You are just driving. So pin number 7, 8, and 9 should be output, right? Set them as output, and then you can have like a while loop. And so if you want to have clockwise rotation, this side should be plus and this side should be minus. And I'm setting pin number 7 high. Pin number 7 is connected to this one, so this one is high and this one is 0, so it is clockwise rotation. Then I have written pin number 9, that is the analog, right? The PWM signal. Pin number 9, you can see this is analog one. It's a PWM channel. So I have written 255, which is it is 100% duty ratio. So D is 100. So which means the motor is fully turned on. So this signal will be like a continuous 5 volt supply. But if you provide this pin with like a 123, so you can achieve like a 50% duty cycle. So the motor will run with the half of its rated speed. All right, that is all about how to control the DC motor using Arduino. If you use a microcontroller instead of the Arduino, only different is these functions will be quite different. You have to connect this enable pin to if you have like a AVR microcontroller, make sure you connect this ENA to the pin that is generating OCX, like output of that PWM signal of like timers and counters, right? There are two ways, like fast PWM and phase correct PWM. So which has dedicated pins for that. You have to connect that or CX pin to this enable, and write a code to generate this duty cycle and the frequency of operation by referring to the datasheet of the AVR microcontroller in Atmel Studio. But we have discussed few examples. You can refer the examples and write the code. But if you use Arduino, that is much more simpler because they have inbuilt function for that. So only adjusting one single parameter, you can achieve the duty cycle. It's much simpler than writing a code in Atmel Studio using a AVR microcontroller. But in some applications, if you want to use a microcontroller other than the Arduino, you have to refer the lecture notes that I have provided for timers and counters and figure it out how to sort it out, this duty ratio and this required pin number. So that this is all about the speed control of and the direction control of a DC motor. And I hope this session is useful for you. Thank you.